Conic sections are made by taking a plane and intersecting it with what we call a double fluted cone. When we do this, we get 7 possible situations. We can get what we call degenerative situations, where we get a point if we just cross through the middle of this. We get a line if we travel right down the edge of this cone. And if we go straight up and down, we just get 2 crossed lines. We don't care that much about those. What we do care about is what happens when we have a plane that is parallel to that edge of the cone, but not on the edge, so we get this parabola there. If we angle it a little bit so it crosses through both sides of one cone, we get an ellipse. And if we make it perpendicular, actually parallel to the base, we get a circle. And if we take that plane and we intersect it up and down, we get a hyperbola there. Two of these. They're not parabolas, they're a different shape, but we get these opposite U's. Okay, so we're going to look at some of these here. And for each of these, geometrically, we call these a locus of points. A locus means a collection of points. So a locus is all the points that make something true here. And we can also define them algebraically through an equation. So, and we can put those together to come up with some good characteristics or useful equations for each of them. So first, we have a general second degree equation. That is this guy right here, where A, B, C, D, E, and F can be constants. And obviously not all 0, but if some of them are 0, and for example, let's say if B, C, D, E, and F are 0, then we get all this would go away, and we have ax squared equals 0. Well, you know what that graph looks like. It's a parabola, and it's a parabola specifically with just one constant multiplier there. So, but if we get if we have more of these that are not 0, then we get different shapes. So first, let's look at a circle. So a circle is the definition of a circle is the set of all points that are equidistant from a center point. So if we find all the points that are equidistant from this center, we might get something like this. Okay, that distance is called the radius. Okay, so here we have all the points that are 5 units away from the point 2, 3. So we've got this point over here that's 5 units away. We've got this point down here that's 5 units away. And all of the points on them, on this red circle, are 5 units away. So using the distance formula, we can say the distance, 5, is equal to the square root of, taking some generic point x comma y, we have x minus 2 squared plus y minus 3 squared. So by the definition of having a constant equidistance there, we can say this is always true. Well, if we square both sides here, we end up with 25 equals x minus 2 squared plus y minus 3 squared. Now notice here that the 2, 3 are the coordinates of that center, and the square root of this is our radius. So our general form for a circle looks like this: x minus h squared plus y minus k squared equals r squared. This gives us a radius of r and a center at hk. So something we want to recognize as the equation of a circle. Sometimes we'll have an equation that doesn't look like that circle equation, but we might be able to change it so that we can find out that it is. So we're going to use some completing the square here. A little flashback. To complete the square, if we have x squared plus bx, we need to add b over 2 squared to complete the square and to make it a perfect square that we can factor. So here we want to complete the square to find the standard form of this circle. Then we'll find the radius and the center. So the key here is this: we have x squared plus 6x plus something, and we're going to leave a blank there, plus y squared minus 10y plus blank equals 2. Well, we would like this to be able to factor into x plus or minus something squared and y plus or minus something squared. So what would you like to have here so that this part can factor? Well, we need to complete the square. Once again, we're going to take that b value and we want to add b over 2 squared. Okay, so if we take this b value, which is 6, 6 over 2 squared is 9. So we want to add 9. Are we allowed to do that? Sure, as long as we do it to both sides. So now this bit right here will factor. This factors into x plus 3 squared. We'd also like to make this something that we can factor. So let's take half of this and square it. Half of negative 10 is negative 5. Square it, we get 25. And we're allowed to do that as long as we do it to the other side. This part here now factors, and it will factor into y minus 5 squared. Notice, by the way, we didn't solve this for y or anything. You might be tempted to put all the x's on one side or the y's on one side. Just leave it alone so we can do this. We have constants. We want the constants on their own side. That's really what we want. Okay? And what does this end up being here? We have 11 plus 25, that's 36. All right, there is our standard form. And so, whoops, let's try that again, see if I can. All right, so there's our standard form. The center comes from the opposite of this. So the center will be negative 3, because this is x minus negative 3, and y minus 5. Okay. And then the radius is square root of 36, which is 6. Remember, our standard form from the previous page there was x minus h squared plus y minus k squared equals the radius squared. And that's what gave us this. Okay. Well, if we take that circle and we stretch it a little bit, we get something called an ellipse. So an ellipse is like this oval-looking thing here, kind of stretched out. And so an ellipse has it has a center, like a circle, it has a center. Okay, but instead of being equidistant from the center, an ellipse is a set of all points whose distances from two fixed points, called the foci, have a constant sum. So wherever the foci are here, which I believe happen to be here and here, okay, so this distance up and over there, the sum of those two black lines is going to be the same as the sum as this blue line and that blue line. All right, so that's how an ellipse is made there. And hopefully some of this is a little bit review. We spent some time in a previous pre-calculus class. So the major axis is the longest chord, and the minor axis is perpendicular to that. So chord goes from edge to edge. So this length right here is our major axis, and the minor axis would be this distance right here. Okay, so those are the major and the minor axis. All right, the foci lie on the major axis somewhere, and we're going to have to find those, okay? And there are two vertices on the major axis that intersect the ellipse. So these are called vertices. Vertices are the ends of this, the four ends of this ellipse there, okay? All right, well, let's explore this a little bit here. So if we take a circle that has this equation, x squared plus y squared equals 16, okay? So let's go ahead and graph that. If we divide it by 16, well, first of all, before we graph it, let's divide both sides by 16, and we get this equation here, okay? Now let's find some coordinates here of some intercepts. So what are the x-intercepts? Well, remember the x-intercepts happen when y is 0. So when y is 0, this goes away, And we know that x squared is 16, so x is plus or minus 4. Okay. All right, what makes the y-intercepts? Well, plug in 0 for x. And what makes this 0? We got y over 16 equals 1, or y squared equals 16. So again, 0 equals x. And we're going to have y squared equals 16. And that tells us that y is plus or minus 4. All right, so with that, we know this is a circle. So if 5 is up here and over here, we have intercepts of 4 and negative 4. So there's a circle there. All right. Approximately. Maybe a little better there. Okay, so we notice this, that in either of these forms here, we can pretty easily find the intercepts, and of course they're going to be equidistant away there, all right? So let's take that now and explore some ellipse and see how this applies to those. So if we change the denominators up a little bit here, we get something like this maybe, x squared over 64 plus y squared over 16 equals 1. So now let's look for those x-intercepts. Well, what makes the y equal to 0? Well, it's going to be x squared equals 64. So x equals plus or minus 8. So those will be our x-intercepts. How about the y-intercepts? Well, let's plug in 0 for x. And if we plug in 0 for x, we have y squared equals 16. And so y equals plus or minus 4. So we're going to be up 4 and down 4. Should put some numbers on these. Okay. Now let's sketch a graph. Well, notice it's not a circle anymore. It's kind of a stretched circle. So what we get is an ellipse that looks like this. Okay, so we get this stretched out circle there, all right? Now we can find the length of the major and the minor axis. Well, the major axis length is going all the way across here. That major axis is 16, right? So that major axis is 2 times 8, which is 16. And the minor axis is 2 times 4, which is 8. Okay? All right. So we have the standard form of an ellipse looks like this. It kind of came from that circle equation. X minus h squared over a squared plus y minus k squared over b squared equals 1. Okay, and if we could flip that around there, okay, here b is the major axis, is why this is written in 2 different ways. Now, we have an important connection, and that is to find the foci, the focal distance C is found, so it's C units from the center, and that's found from C squared equals A squared minus B squared, okay? And where that comes from is this. So there's a focus here, and this distance C is related to the semi-major minor axis, so that we'll call that A. And we can prove that this B distance is the same as this distance all the way out to here. We won't at this moment, but you can prove, that might be a good one for you to prove to yourself that that's the same. So in this case, we see that A, which is the minor axis, or the semi-minor, half of the minor axis, plus C, the focal length, equals C squared equals B squared, the major axis. Okay. We can also solve that C squared equals A squared minus B squared. All right. So if we want to find the center, the vertices, and the foci of these ellipse, then we can go ahead and we want to complete the square here again. So let's get all the x's together. Let's move the 8, move this 8 to the other side. Let's get the y's together. And let's complete the square. What would you like to have here? Well, the challenge here is we've got this 4 here, so we're going to need to factor this out. 4 times x squared minus 2x, y squared plus 4y. Leave a space there. And now we're going to complete the square, all right? So we would like to add half of this squared, which is 4. Let's add 4. Now we want to add half of this squared, that would be 1. But what did we add there? We didn't really add 1. This is really 1 times 4, so we need to add another 4 there. Okay? And so now this is 4 times x minus 1 squared plus y plus 2 squared equals 16. And finally, we want to make this equal to 1, so we're going to divide by 16 everywhere here. And we have x minus 1 squared over 4 plus y plus 2 squared over 16 equals 1. We're now in the standard form, so we can now see that this is our the square root of 4. So a is the square root of 4, which is 2. And so and let's go here. B is the square root of 16, which is 4. So the minor axis is going to be 2 times that, which is 4. The major axis is going to be 2 times 4, which is 8. And last but not least, we know that c squared equals a squared minus b squared, which is... Well, we got to fix this here real quickly. This is actually supposed to be... Let's see. This is supposed to be b, and this is supposed to be a. It doesn't really matter. Technically, a in all these expressions is the largest one. So c is that distance right here. So if this is a, that's c. So c is the focal distance, and a would be the largest distance, and b would be the smallest distance there. So what matters is that the a is always the larger of the two axes. All right, so it's the major axis. So anyways, in this case, we got 4 squared minus 2 squared, which is 16 minus 4, which is 12. So c is the square root of 12, which is 2 square root of 3. All right. So again, c is that distance from the center to the foci, and a is that longest distance that goes all the way out to the major axis. Okay? And it turns out that a is also that hypotenuse, but that's not where it comes from. So it comes from the major axis, or the semi-major axis. So the last part here is, the last feature, I should say, of an ellipse is eccentricity. Eccentricity tells us how stretched out an ellipse is. All right, so eccentricity is going to be a ratio of c to a. So we got c to a. Well, again, c is the distance between the foci there. And then a is the semi-major axis. So a is this distance here. That's a. All right? So c is always smaller than a. So this is always going to be less than 1. Now, when this is a circle, since we know that a is the largest number here, we know that a squared equals b squared plus c squared. That's the picture we had earlier. All right? So b is this distance here. So b is here. Okay. And so we had this relationship of A, B, and C. All right, A is also this hypotenuse of this triangle. So anyways, when this is a circle, then A and B, the axes are the same. So since these axes are the same, then C equals 0. So if C equals 0, then we have a circle. So the shape is a circle. So the closer it gets to 0, the closer it is to a circle. So if we look at the last problem we had here, we had an A value. A is the semi-major axis, and that is the square root of 16, which is 4. So the eccentricity here is 2 square root of 3 all over 4. Also known as the square root of 3 over 2, which comes out to be about 0.8660. Okay? So that's kind of stretched out there, all right? We have one axis of 4, the other axis of 2. So the major axis is twice as long as the minor axis. Well, if we take that and we kind of compare that to the eccentricity of the moon and the other planets, the eccentricity of the moon is 0.05. But here's the 8 planets that have an orbit of, a eccentricity of 0.2 for Mercury, 0.00 for Venus, 0.1 for Earth, 0.9 for Mars. Again, the closer to 0 it is, the closer to a circle. So Venus is pretty darn close to a circle. Okay, and in fact, most of these, notice 0.0, they're pretty close to circular. Mercury is the one that's the most stretched out there. So it'll have the most extremes in its, I guess, its weather as its distance from the sun gets more stretched out. Okay, but Earth is pretty close to a circle, and so you might think about, well, why do we have seasons? Is it because of the oval nature, the elliptical nature of the orbit? No, it's actually not so much that. Seasons are more from the tilt of the Earth than the actual elliptical orbit around the sun. So, anyways, so those are the main features of an ellipse. Eccentricity tells us how stretched out it is. The major axis A is the longest distance, so that's the semi-major axis is A. B is the semi-minor axis. C is the focal distance from the center to the foci.